Hello class, welcome to our guided notes session on Skill 5 from Unit 4. We're still in the graphing mode, okay, but now we're going to be graphing the cube root function. Cube root function is indicated with a radical sign and a little teeny index, we call that, of 3. We kind of write it as a little bitty number sort of right outside of the radical sign. It's called the index. So when you see a 3 out in front, we understand that we're taking a cube root. Okay, so what is a cube root? It's helpful to know that if we're going to graph a cube root function. It's the cube root of a number x is whatever number you would have to multiply to itself 3 times to equal x. For example, let's say I'm taking a cube root of 27. It would look like this. I'd have my little square root sign, a little 3 out in front, and then 27 under the radical sign. So what I'm supposed to look for is a number that when you multiply it to itself 3 times, 3 times 3 times 3, is equal to whatever that number is inside the radical. So in this case, the answer is 3, because 3 times 3 times 3 produces 27. So therefore, 3 is the cube root of 27, because that's the special number that would need to be multiplied to itself 3 times to equal 27. And then I just did another one for you to get an idea. So if you see an index of 3 and then this number inside, I'm looking for the cube root of 1,000, which ends up being 10, because 10 times 10 is 100, times 10 a third time would produce 1,000. Therefore, 10 is the cube root. It's the number that would have to be multiplied 3 times to produce this number under the radical, which was 1,000. Okay, the other thing I want to point out is that a cube root of a negative number is a real number. You don't have to worry about imaginary numbers when you're taking a cube root. You can plug negatives under the cube root sign. And the reason for that is because if you multiply a negative number to itself 3 times, the answer will still be negative. For example, I just chose negative 5. If you do negative 5 times negative 5, the first 2 will become positive because those first 2 negatives will cancel to give you positive 25. But then if you multiply that to a third negative, it creates a final answer that's negative. You have positive 25 times negative 5, you get negative 125. So when you're taking the cube root of negative 125, we just know, oh, that would be if I multiplied negative 5 to itself 3 times. It's a real number, right? I don't have to worry about it being some sort of imaginary number, okay? And then related to that, on the same line, I know that cube roots are either only ever going to be positive or negative, not both, because the cube root of a negative is negative. The cube root of a positive is a positive. It's never both, like a square root used to be, okay? And I gave an example here. So if I'm taking the cube root of positive 1, that could not be negative 1. It has to be positive 1 because 1 times 1 times 1 is 1. Negative 1 times negative 1 times negative 1 is negative 1, not positive 1. You know, so back in the day with square roots, we'd say, oh, the square root of 1 is positive or negative, right? You could take a positive or negative 1 because negative 1 times negative 1 was 1 and positive 1 times positive 1 was 1, right? But this is cube root. It doesn't work the same way. You multiply a negative 3 times, you'll get a negative. So the cube root of 1 is only positive 1, not both. And similarly, back with square roots, if we were trying to take a square root of a negative, specifically negative 1, we used to call that I. Because if it's a square root, there is no way to take a square root of a negative and get a real number. It's not possible, right? Real numbers, if you multiply 2 negatives, they become positive. But we don't have to worry about that. We don't have to worry about imaginary numbers with odd roots. So that's something to be celebrated, right? Yay, no imaginary numbers. Because it's easy to find a negative cube root. You just make it negative. Negative 1 times negative 1 times negative 1 will equal negative 1. Therefore, the cube root of negative 1 is simply negative 1. It's not I. Okay? So actually, I find cube roots easier, to be honest with you, than square roots. It's very straightforward. I don't need to worry about imaginary numbers, and I don't need to worry about having positive and negative roots for the same input. Okay? So with all this in mind, let's go ahead and compute this table of values over here. So we're taking cube roots, right? That's what y equals. It's the cube root of whatever these inputs are. So notice the inputs. I chose them specially to make it easy to take the cube root. I told chose numbers that are perfect cubes, so that when I have to come over here and take the cube root, I could easily find a number that multiplies to itself 3 times to equal. So negative 8, the cube root of that will be negative 2. And the reason for that is because negative 2 times negative 2 times negative 2 equals negative 8. Okay? Negative 2 is the cube root of negative 8. And then the cube root of negative 1, we did that one down here, is equal to negative 1, right? Because negative 1 times negative 1 times negative 1 equals negative 1. So negative 1 is the cube root. The cube root of 0 is 0, because 0 times 0 times 0 is equal to itself, 0. So it's its own cube root, just like negative 1 is its own cube root. And the cube root of 1 works similarly. It's just 1, right? 1 times 1 times 1 is 1. We kind of looked at that right here. So these two, the input and output will match. These three, actually, negative 1, 0, 1, the input and output will match. And then the cube root of positive 8 would just be positive 2, because 2 times 2 times 2 is equal to 8. Therefore, the cube root of 8, the number that multiplies to itself 3 times to equal 8, is 2. Okay? So these are my outputs, negative 2, negative 1, 0, 1, and 2. These are the cube roots of negative 8, negative 1, 0, 1, and 8. So now I'm going to graph them down here, and I will start with this first one. So negative 8, negative 2 is right here, and then I've got negative 1, negative 1, 0, 0, which is right at the origin, 1, 1, and then positive 8, positive 2. And it's going to kind of look like that. So it's increasing ever so subtly. The y is slightly moving up as x goes right. And on this side, the y is ever so slightly going down as x goes to the left. So it looks kind of like a linear function with a very small slope, except it's not linear. Okay, it does have a slight subtle curve in here. So don't forget that. Don't draw it like a line. Draw it like a nice subtle curve. Now, before we do these defining characteristics down here, let's take a moment, pause for a moment, and just consider the relationship between the cube root of x and x to the third power. The graph of x to the third power was something we had learned to graph in Unit 2b. It was the very end of first semester. I want to revisit that function for a moment. This was the function where I would take my x's and cube them. It was the x to the third parent function. So I just used, in all of semester 1, these were the x's I used for all our parent graphs, just negative 2 to 2. Just the numbers right around the origin, a couple negative, a couple positive. And I just cubed them. I just raised each of them to the third power. And so to do negative 2 to the third, we just multiplied it to itself 3 times and got negative 8. And then for negative 1 to the third, I multiplied negative 1 to itself 3 times and got negative 1. And so on, right? 0 times 0 times 0 was 0. 1 times 1 times 1 was 1. And lastly, 2 times 2 times 2 was 8. So I had negative 8, negative 1, 0, 1, 8 as my outputs. And then negative 2, negative 1, 0, 1, and 2 were my inputs. So I want us to just look at that for a moment. Compare inputs and outputs from both of these functions. And I'm hoping you're noticing it right now. Maybe you already noticed it even before. But they're the same numbers. They've just switched roles. What used to be the outputs from the original cube function, x to the cube, negative 8, negative 1, 0, 1, 8, are now the inputs of my cube root graph. And the outputs of my cube root graph, negative 2, negative 1, 0, 1, 2, are what used to be the inputs from my x to the third graph. So what does that mean? That means these functions are inverses of each other. So x to the third and cube root x are inverse functions. Okay, they're both functions because x to the third is a one-to-one function, so its inverse is going to be a function. You can see its inverse is right here. Passes the vertical line test, no problem. But it's really helpful to understand that that's the relationship. The cube root is just the switching of the input and output, of the x cubed graph. And so it's really nice to see when they're on the same grid. So let's just do that. This will be the only time really we have the time to kind of look at it. So let's do it. So I'm graphing x to the third, which has a point at 0, 0, 1, 1, 2, 8. It also has a point at -1, -1, and -2, -8. So we used to call this the squiggle graph, if you remember. For lack of a better word, we called it the squiggle. That was x to the third. And then if you put that on the same grid as cube root, that's this one right here, cube root of x, where it's same x and y's only switching, right? So instead of 2, 8, it's 8, 2. Instead of -2, -8, it's -8, -2. Of course, these 3 points are all the same because x and y are equal. And then it kind of goes like that. Ever so subtle curve, just like in the squiggle graph, it was an ever so subtle curve right around the origin. And then if you look at that y equals x line, just sort of cuts them both in half, you'll see that these 3 points, the -1, 0, 1, is where they wrap around that line. They kind of intersect on that line right at those 3 points. Anyway, you can see that beautiful y equals x symmetry right there. So nice. And then you can really also see the cube root, how it really is a reflection of x cubed over that line y equals x. So you can really kind of think of this graph as a sideways squiggle. I'm probably going to call it that because sometimes it's easier just to say that and then you can kind of picture this. It's what used to be this graph going up and down with a slight curve in the middle, but now it's just facing right and left with a slight curve in the middle because it's the same points, just x and y have switched. So we got that down. These are inverses of each other. We're looking at a sideways squiggle now. So now we can kind of talk about these defining characteristics. Well, here's what I love about cube roots and x to the third is that everything's allowed to be negative. There's no rules about the, what you can plug into a cube root. You can plug in negatives if you want. Out will come negatives. Domain and range can basically include everything. Nothing's off limits. It just makes for a much easier graph. The x and y intercepts for both, for the sideways squiggle for my cube root is they both go through the origin right here at 0, 0. Now for the parent function, this function is increasing the entire time. If you read it from left to right, as x goes from -infinity and approaches positive infinity, the y values ever so subtly increase. Not very fast, but they still get bigger. They increase, okay? And then since we only read graphs from left to right when we're talking about increasing or decreasing, we would say this graph never decreases. The parent function doesn't anyway. And then the point of symmetry on the parent graph is 0, 0. In general, that'll be your HK. Your HK will kind of determine the middle of the graph, which is where that subtle curve kind of happens and where the graph has symmetry around the origin. Has point symmetry around the origin 0, 0. And yes, yay, this cube root is also 1 to 1. The x cubed graph was 1 to 1. It passed both vertical and horizontal line tests. So when you invert it, it'll continue to pass both vertical and horizontal line tests. So yes, it's 1 to 1. All right, so as you know, with all of our parent functions, we start with the simplest form, right, parent function. But then we allow there to be some transformations, we call them, right? We tell you to describe the transformations, and we look at things that are in this format. We call it HK form, where you've got A being multiplied on the outside, H is being subtracted underneath the radical sign, K is being added to the outside. These 3 things all have different effects on the graph. So the A, just as a reminder, vertically reflects if it's negative, vertically stretches if the absolute value of it's positive, vertically compresses if the absolute value of it is between 0 and 1. And again, that's because the A value is multiplying to the y, right? Multiplies to the y. That's what makes it have such power to reflect, stretch, and compress. It can actually change the width and even reflection of the graph. Okay, but H, okay, that's this guy on the inside here. following the subtraction, right? Which is why it's always opposite of what you might think, because it's coming after a subtraction. But it will make the graph move either right or left. It is a horizontal shift, left or right, okay? The y value, the k value, that's this guy being added outside, is going to vertically shift and make the graph either go up or down. Now remember, h and k do not affect the shape at all. They only affect the location, right? They move, h and k move the point of symmetry. They move the middle to h and k. But they don't change the shape. They can't reflect it, stretch, or compress it. Only a can do that. And that's because these things are being added or subtracted. So this adds to x, and this adds to y. So that's the transformations that we're going to be looking at, all right? The steps are identify the parent. Always identify the parent, which in this particular section, this notes is always cube rooting, x. Cube rooting, okay? So that's where your x's are -8 to 8 and your y's are -2, -1, 0, 1, 2, because we're cube rooting the x's. So we make the table of values right here, okay? Then we're going to identify a, h, and k, and then add h to x, multiply a to y, and add k to y. Then we graph the new points, and then find all of the things. Let's try it on the back. Okay, in example 1 here, I can see my a value is 0.5, right? That's the number on the outside of the cube root multiplying to the cube root. I can see my h value is 1 because I have that number being subtracted from x under the cube root. And k must be 0 because nothing is added. So we can think of that as saying plus 0. So what I'm going to do is start with the table of values for the parent function. Okay, start with the table of values for the parent function. That's where I had all these perfect cubes for x. And then I cube rooted them for y. Right? Cube root of -8 was -2. Cube root of -1 was -1, and so on. So these are the x's and y's from my parent function. Okay. Then I add h to all of my x's. And I multiply a to all of my y's. I didn't have to add any k because k was 0. If I did, I would add that after I multiplied them all by a. So my points turn out to be, so this would be -7, half. 0.5 times -2 is half of -2, which is -1. And then this point would turn out to be 0, half of -1, which is -1/2. This point would be 1, 0, because half of 0 is still 0. This point would be 2, positive 1/2, right? Half of 1 is positive 1/2. And then this last point would be 9, 1, because half of 2 is 1. So these are my new points. And then notice the middle point, 1, 0, is my h and my k, right? 1, 0. The middle point should be hk because that's your point of symmetry. That's your point of symmetry, okay? All right, so let's plot these points and see what happens. So I've got -7, -1. 0, -1/2. Oh, right there. 1, 0, 2, 1/2. And 9, 1. So it's ever so subtly going to curve right through that HK point, right through my point of symmetry, which is right here at 1, 0. That's where you'll see the slight curve happening, which I know is really hard to see because this has had a vertical shrink, right? This has been vertically shrunk by 1/2. So it was already kind of a flat graph to begin with, and then I shrunk it, making it even flatter. but we want to make an ever so subtle curve happening right around the HK as much as we can. So we get that sideways squiggle going on. Let's look over here at the graph in part B of example 1. So I can see I've got an A value of -3, right? Let me write that down here. I have an H value of 0 because the radical sign stopped after the X, so nothing's being added under the radical sign with X. So that means H is 0. And then K is 2. K is plus 2. Because that's being added after the radical sign ends, it's being added to the outside, so that's the K value. So before I deal with those, I'm going to make my parent table of values, right, which is just cube rooting X. So I choose all those perfect cubes for X to make it super easy to cube root them. So cube root of -8 is -2, cube root of -1 is -1, 0, 1, cube root of 8 is 2. And so those are our parent table of values. Now I don't have to add anything to X because H was 0, but I do need to multiply the Y values by -3, and then after that add 2. Okay, so this will produce 5 new points. So they will be -8, comma. So this is 6 plus 2 is +8. And then -1, comma, 3 plus 2 is 5. 0, comma, 2, right? Because -3 times 0 is still 0. 1, comma, -3 plus 2 is -1. And 8, comma, -6 plus 2, -4. So I have all these points here. And I'm going to go ahead and plot them. But before I do, I want you to pay attention to that middle point, right? That should be my HK. That should be my point of symmetry. It should match what you have for H and K, and it does. So that'll be my middle. That'll be where the subtle curve happens, okay? And let's plot these points. So -8, +8 would be up here. -1, +5 is right here. 0, 2 is right there. 1, -1 is right there. And 8, -4 is there. And so it kind of goes like that. It's actually not so subtle, right? The squiggle part becomes, well, vertically stretched. It's been amplified, you could say, because it's had a vertical stretch by 3. But also the part that goes up it's been reflected, right? If you compare this to this one, the positive Y values are actually on the left side where X is negative, and then the negative Y values are on the right side where X was positive. So it's had a vertical reflection, right? It's had a vertical reflection flipped over the X axis, and it's had a vertical stretch because the A value is 3. Aside from being negative, it was 3. So it kind of extends or stretches the graph. And so then it's not such a subtle curve. It becomes a much more obvious curve. Okay, I want you to try some graphs on the back, and we will save all of these defining characteristics for our next video. Okay, so we won't do this in this video, but I want you to go to the back and try graphing these equations back here. Pause your video, come back and check your answers. Welcome back. Let's see how you did. So for the first you try, you have quite a significant stretch of 4 and a vertical reflection. So your graph should look like this. The sideways squiggle has sort of flipped over the x-axis, and it should be very stretched out and like amplified. Okay, so the curve is very obvious. These were the points I got: -6, 8, 1, 4, 2, 0, 3, -4, 10, -8, based on these transformations here. And then here's my curving. The middle is right there at 2, 0 at my HK. That's where you kind of notice the curve transitions. Instead of opening down, it opens up. That's where the change in curve happens. For the second one, it was like a majorly shrunk, right? It had a vertical shrink by 1/3, so it almost looks like a flat line, almost. It's a very subtle curve. The middle of the curve is happening at -1, 5. Right, that's your middle, that's your HK. That's where, if there is any curve, it's going to be happening right around there. It's kind of hard to even show it because the points are all so close together. I've got them right here. 4 1/3, 4 2/3, 5, 5 1/3, 5 2/3. So those are all very close together. Not a lot of change, but you can see the y values do slowly increase, right? They do creep up slowly, but surely. They're going up by thirds, right? Anyway, so there's our graph there. So hopefully you were able to get those. If not, I can help you out in class tomorrow when we do more practice, and I'll see you there.